This is section 6.4, and we're talking about exponential growth and decay. A lot of this topic you've already had in pre-calculus, but there are some calculus aspects to this topic that we have to look at. So the essential question is, how can logarithms and exponents be used to solve differential equations? And so when we talk about exponential growth and decay, a lot of times we're talking about a population, and so in this case, bighorn sheep, or we're talking about things like decay, radioactive decay, or interest rates, growth in investment, or something like that. So those are kind of going to be the three things we're going to look at. So the first thing we're going to look at is this sort of relationship here. So a rate that is proportional to the number of sheep present. So in other words, a rate, when I say rate, rate's like a rise over a run or a slope. So this is a derivative, and the derivative is proportional to the number of sheep present is basically the value of the function. So we have a derivative proportional to the function value. So the first example is going to talk about bighorn sheep, and so we have a population that increases at a rate as proportional to the number of sheep present. Like I mentioned, this happens with all living creatures. So in other words, this relationship basically says the more sheep we have, the greater the rate of producing sheep is. And again, we I know I said this earlier, but this also exponential models also explain radioactive decay and interest rates and financial investments. So this is the differential equation for this very specific relationship, where the rate is proportional to the amount present. So here's the rate, here's the amount present, and here's a proportionality constant. And this is the beginning of your notes. This is the box in the top left corner of your notes. So if we have this very specific relationship, where k is a proportionality constant, so k is a number, then we know the solution is exponential. So the function that describes the population is equal to some initial value times e raised to the power of the rate constant times time. And we'll just take a second here to look at this. If I had P, E, and R and T for interest, we could see that this is the PERT equation. And we'll kind of come back to that a little later on. But what we're going to do is, like I said, this is a very specific relationship, and the relationship is described by this phrase, okay, rate of change proportional to the amount present. And we're going to solve this. This differential equation is separable, and so we're going to separate it and solve it the long way. And we're only going to do that once. After that, you're going to just jump to the shortcut here, knowing that the function itself, the solution to this differential equation, is just this exponential relationship. So we have a rate of change, we have a proportionality constant, which is just a number, and we have the amount present. And so when we look at the function itself that describes the population, the rate constant that goes up in the power, and this y sub 0 is the initial value. So if we go back to this example that you have in your notes, we have bighorn sheep, and they'll say the population increases at a rate that is proportional to the number of sheep present. Once you see that phrase, you know it's this. Okay, and then the example goes on to say that the rate constant is 1/10, and the initial population is 1,500. So with these two values, we should be able to write both this and this. So the differential equation is going to be dy dt equals ky. Well, k is the constant, the rate constant, so this is 0.1 or 1/10 times y. And then the function itself, knowing that the initial value is 1,500, the function itself then is going to be the initial value, which is 1,500, times e raised to the constant times time. So that's going to be 1/10 times t. So this is what you're going to be doing by the end of the lecture. But like I said, just once, and then you've got some space on the right-hand side of this box in your notes. We're going to separate that differential equation and solve it the long way, just to show that we end up with this. So let's start with this differential equation. And in order to separate it, we need to get all the y's on one side and all the t's, in this case, on the other. So this is a dy dt problem, kind of like a dy dx, but since we're talking about things that are time dependent, we use the variable t. So the first thing we're going to do is multiply both sides by dt. It's going to cancel out over here. We're going to have our differential dt over here. So we're going to have something that looks like this. And now we need to get this y over here. So we're going to divide both sides by y. It's going to cancel here. And we're going to have, this is just 1 over y times dy. And this will be 0.1 times dt. And these y's cancel. So this is the key right here. I want you to focus on this left-hand side here. 1 over y dy, when we integrate that, is the natural log of y. And it's this arrangement that gets us that natural log antiderivative. And that's really key. That's the whole reason why this ends up being exponential, because in order to solve for y, we're going to have to exponentiate both sides. So we have natural log of y equals, and then the antiderivative of that is going to be 0.1 t. And then, of course, since we're taking antiderivatives of both sides, we have a constant of integration. So this is the calculus. We're done with the calculus at this point. The rest of it is just working with a natural log expression and solving for y, which is what you've done in pre-calc. So we're going to take that relationship now and solve it for y. And that involves exponentiating both sides. In other words, making each side a power and e the base. And we need to use e for the base because this is a natural log, and this logarithmic identity equals just y. Now, when we raise this to a power, our laws of exponents says if we have a single base and a power that's more than one term, we can have the same base and give each power its own base. And so that's key in the solution to this, to get it into the form that we saw on the other slide, because we know Euler's number E is just a number. It's about 2.7. If we raise it to a constant, then this whole thing just becomes another number. And so we're going to call this whole thing just C. And so the form, if we call it just C, then the form is then going to be C e to the 0.1 t. And at this point, we can really drop the absolute value signs because this exponential relationship won't ever be negative. And when we're talking about population growth, we always have to start with a positive number of animals or people or something. So we're going to take this now and solve for that constant of integration. So we have an initial condition here. The initial condition is that when at the initial population, which means when t is equal to 0, we have 1,500 sheep. That's the initial population. That's what that means. So we're going to go ahead and put 0 here and 1,500 here. And e to the 0 is 1. So we have a constant of integration here of 1,500. In other words, that number out in front is going to be that initial value. You know, as we have in that box at the beginning of your notes for the law of exponential change. So the function then that describes the population of sheep is going to be 1,500 times e to the 0.1 t. So if you notice, we got what we were able to write an expression for using the law of exponential change. And so that's kind of going through it the long way, separating and integrating that differential equation. And at this point, you don't need to do that with this relationship anymore. So what we're going to do is we're going to try starting with the differential equation and getting our function our exponential function, and this is another kind of on the quick sort of thing. In other words, we're going to develop this shortcut. And so, so we have a box in the middle of our notes on the front page that says the law of exponential change on the quick. And the first one is dealing with all variables. So what happens when our differential equation looks like dy dt equals ky? And again, since most of these are time dependent, we're not really describing anything dy dx. We're using dy dt. And let's have our initial condition be y sub 0 when t is equal to 0. Then we don't need to separate and integrate. We know the function is going to be the initial value, which is going to be y sub 0, times e. And then the power here is going to be k times t. So we're going to pull that k over from the differential expression and multiply it times t. So the idea is when I have the differential equation and initial condition, if I have these two pieces of information, I should be able to write this without using any calculus. Okay, and for this very special situation, when we have the rate of change proportional to the amount present. And we know we have that situation because we see this. We see the rate of change, here's our proportionality constant, and here is the amount present. So let's try this with some numbers now. Let's say the differential equation is 2y. The initial condition is that we have 7 of something at the beginning. So our exponential function then is going to be 7e, and then we're going to take the 2 and bring it up into the power. So it's going to be 7e to the 2t. Let's try it again with the next set of differential equations and initial conditions. So here's our next differential equation, 5/3 y. Our initial condition is that we start out with 10 of something. So our exponential function is going to be then 10e to the 5/3 t. Okay, and let's try that last example. Here's a negative proportionality constant, and that's okay. Negative just means we have decay instead of growth. Our initial condition here is we start with 23 of something, and it's going to decay. Then our function that describes that decay is going to be 23e to the negative 0.7t. And so, like I said, when we have this very special situation of with the rate of change being proportional to the amount present, we don't need to use any calculus at all. We know what the function is going to look like. So you might think, well, where's the calculus? And the calculus will come along on the back side. But before we get to that, we're going to talk a little bit about decay and interest rates. So, and this is all pre-calc. So you might be able to bust through this pretty quickly. Or you might need to pause the video to kind of think about when you learn this in pre-calc. So we know that when we have radioactive decay, we know we're losing a quantity. It's getting smaller and smaller. So when we start out with something, if we start out with a value and we end up with less, then that means we're dealing with a negative power out here. And so typically with radioactive decay, we write it with the negative power right here so that the value k can still be considered a positive number. So let's talk about half-life. So the half-life is the time required for half of the material to disappear, basically. So let's start with this general equation. If we start out with y sub 0, then if we're trying to find a half-life, then we're looking at when there's only half of it left. So we're looking at when we have half y sub 0 left. So we're going to figure out the half-life, how long it takes for half of it to disappear. And if we notice, we can cross off the y sub 0 variable, and we end up with the natural log of half equals the natural log of e to the minus kt. So this is definitely a pre-calc thing you did. But you know, in order to solve for t, we need to take the natural log of both sides to get the exponential function. Take the inverse of the exponential function. That's what we're doing there, because natural log is the inverse of the exponential. That allows this power to come down in front. And this ratio here, we're also going to apply a log relationship here. If we have the natural log of a ratio, we can take the natural log of the difference of the numerator and denominator. And then bring the kt down in front gives us kt times natural log of e, which is 1. So we just have negative kt. Natural log of 1 is 0. So we have negative natural log of 2 equals negative kt, and I'm going to go ahead and divide out the negatives, and then I'm going to solve for t. So here is a way to find the half-life. Notice when we're talking about half-life, we have a natural log of 2 in the numerator. So natural log of 2 divided by k is going to be the half-life for anything that's radioactive. So anything that's decaying, basically. So that half-life then is dependent upon this constant rate. And so we're gonna, that can go ahead and go in your box at the bottom of the first page. This should have been on that left-hand side of the box. And then on the right-hand side, we're gonna look at this example as the scientists who do carbon-14 dating use 5,700 years for its half-life. Find the rate constant. So we know the half-life is 5,700 or 5,700 years. And so we want to find the constant. So we know we're going to have a tiny constant. It's going to take a long time to lose half the carbon-14 molecules. So the rate constant then k is the natural log of 2 over 5,700, which ends up being a pretty small number. I don't think I have the number in the PowerPoint, but that ends up being, let's see, natural log 2 divided by 5,700, that ends up being 1.216 times 10 to the minus 4th. And then the example goes on to say, find the rate constant, excuse me, find the function that models the decay of 20 grams of carbon-14. So in other words, I want a function that's going to model 20 grams decaying. So we know we start out with 20. It's going to take 5,700 to get down to 10 grams of carbon-14. So our start value is 20 grams, e to the kt. And we're going to have a minus sign there. And so I'm just going to put in minus natural log of 2 divided by 5,700, this whole ratio, times t. You could put it in the decimal equivalent as well, but you don't have to. So here's the function that models the decay of carbon-14, radioactive carbon. Notice we jumped right from the we jumped right to the equation. We didn't have to do any separating or integrating because it's that we know that radioactive decay, it follows that proportionality relationship that we're focusing on right now. The other thing that follows that relationship is interest-bearing accounts. So suppose we deposited, and this is the top of the back page now of your notes. Suppose we deposit $1,000 in an account, pays 6.3% annual interest. How much will you have 8 years later if we compound continuously? And so since we're compounding continuously, we have, again, that exponential relationship where we have that the future value equals the initial deposit times e to the r times t, where r is the rate, which is basically your PERT equation, if you remember that from pre-calc, and I even think you had that in Algebra 2 as well. So, so we know that we start out with $1,000. And we're going to, if we want to find how much we have 8 years later, we're going to multiply that times e to the RT. R is the rate. And we need a rate that's in decimal form. So that's going to be 0.063 times 8. So in 8 years, we're going to have $1,655.33. Here's another example, finding out how long will it take for your deposit to triple. Well, if we started out with 1,000, so here's the function that describes how that $1,000 grows over time. If we want to triple our investment, that means we're going to look and see how long it takes to end up having $3,000. So we're going to solve this for t. So in order to solve this for t, we're going to have to isolate the exponential, which means dividing out by 1,000 first. And then we're going to have to get the 0.063 times t out of the power location. So we're going to take the natural log of both sides. And then when we bring down the power in front of the natural log, we know the natural log of e is 1, so we have 0.063 times t. We can divide out the 0.063, and we can find out how long it takes for our investment to double. If you notice, this ratio here looks a lot like the half-life expression, except there's a 3 there because we're talking about tripling, but it's still ln of a number over k. So when we're talking about half-life, it's ln2. When we're talking about, because that's, you know, waiting to see how long it takes for half of it to disappear. And it's decay, so those minus signs cancel. When we're talking about tripling our investment, it's going to be ln3 over k. If we want to quadruple our investment, it's going to be ln4 over k. If we want to see how long it takes to make 10 times that much, to grow it 10 times as much, it would be ln10 over k. So that's a quick solution for those tripling and quadrupling questions. But the solution's not too long anyway. So going ahead and plugging that into your calculator, we end up with about 17.438 years for the triple. So if it takes 8 years to get $1,500, which is halfway here, takes a little over 17 years to get the $3,000. So this is kind of the meat and potatoes for the calculus applications of exponential expressions. Instead of having dy dt equals k times y, so instead of having that rate proportional to the value, we have something that looks like this. So we have the rate and we have no proportionality constant. And in fact, not only do we have no proportionality constant k, but we have x's and y's over here. So we no longer have that special relationships that allows us to sidestep the calculus. Now with this sort of scenario, we have to do the calculus. So before we jump into doing the calculus, let's take a look at the slope field first. So if we talk about this differential expression, and I've got 4 options here, and I think actually on your paper they didn't print out too well, so on the screen they probably will look a little better. Let's try to pick out the slope field here. So remember, we're going to look for those special values of where the derivative is 0, what makes it 0, what makes it vertical or undefined, and what makes it -1 and +1, if we need those last 2 values. So if x is 0, then this is 0. So we have to look for value. Now 0 slope is a horizontal line. So x equals 0 is this axis here. So if you notice on option A, when x is 0, the derivative is 0. So we're looking for a horizontal line. We have a horizontal line here in option A. So that's possibly a correct solution. We also have a horizontal line here in option B at x equals 0. So this is a possibility. We have vertical lines for option C, so this is out. Go ahead and put an X through option C. In option D, same thing. We have vertical lines here, so this is out because that's not 0 slope, that's undefined. So we know that. So this is okay, this is okay, this is out, this is out. Okay, how about when this is 0? So this is 0 when y is 6. And so we're going to look for those horizontal lines at y equals 6. So here's horizontal lines at y equals 6. So that's potentially a solution. Again with B. So that doesn't help us at all because we still have those. Now anytime we have a horizontal line along a grid line that's also horizontal, that becomes an asymptote. So if you notice that solutions up here are going to stay up here and solutions down here are going to stay down here, and likewise on this picture. So now we have to start looking for some other things. And I'm going to look for where this is positive or negative because it's a product of two things. So when x is positive and y is bigger than 6 means up here. Okay, x is positive means over here. So these two areas are when x is positive and y is bigger than 6. So x is positive, y is bigger than 6. That's going to make this positive, and bigger than 6 means this is either 7 or 8 or 9. This is going to be negative. And so I'm going to look for things that slope in the negative direction. These are all sloping positive. These are all sloping negative, so this has to be the right answer. So we're going to X out A. This is our correct answer. So we know slope, the option B is the correct slope field. Now let's go ahead and solve that differential equation. So the first thing we're going to do is multiply each side by dx. They're going to cancel on the left. So we're separating our variables here. And that first step is always multiplying by dx. So we have dy then equals x times 6 minus y times dx. So our x's are all on one side. Now we got to get this y over with the dy. And we've got to take this whole group. Because of this minus sign here, we can't just divide out the y because we can only divide factors. And so we have x as a factor, dx is a factor, and this whole thing in the group is a factor. So we're going to divide by 6 minus y. And so we end up having dy over 6 minus y, which is the same as 1 over 6 minus y dy. Okay, it's the same as that, equals x dx. Those cancel. And we're going to integrate that, or do the antiderivative. Now remember, these sort of relationships lead to exponentials. Okay, when we have a combination of an x and a y multiplied together on the right-hand side, we're always going to have a y in the denominator. We're always going to have to divide out that y. So that's going to lead to an exponential solution every time. So think back to just envision this being just an x, 1 over x. The antiderivative is the natural log of x. So this is going to be integration we want to do on the quick here. So this is going to be 1 over integrating this 1 over 6 minus y is going to be the natural log of 6 minus y. And whenever we have a single a variable to the first power, we end up with a natural log, just like a 1 over x. Now, this isn't on the quick one. This is a linear factor. Remember our on the quicks with linear expressions? We just end up dividing by the derivative of this, which is -1. So we want to kind of do that on the quick, and this will always end up being, with this exponential relationship, this will always end up becoming a natural log, and then we just have to look to see if there's a derivative that's that we need to take to divide out. And then the antiderivative of the right-hand side is x squared over 2, and then plus c. And, and so here's our antiderivative, and so we have to solve this for y. So this is the only calculus step here. And we're sort of kind of done with the calculus, but there's still a lot of math to do here, and it's not exactly easy math either. It's pretty high-level math. So the first thing we're going to do here is we got to isolate the natural log here because we have to solve for y. So we're going to multiply each side by -1. So when we do that, we get the natural log of 6 minus y equals negative everything else on the right-hand side. And then we have to exponentiate because we need to get rid of this natural log. So it's going to look like this. E to the natural log of 6 minus y. So exponentiate means make this an exponent and make this an exponent. And that's exactly what we did here. We made each side an exponent. That allows this side to be called 6 minus y. And that allows the other side, now I'm going to do the same splitting of powers. So I'm going to give each its own base. So this is minus x squared over 2. So that gets its own base. And minus c gets its own base. I have a typo here. That should not be there. So this should be minus c. And then we're going to solve this for y. So in order to solve this for y, we can bring the y over here and bring all of this stuff over here. Okay, because this y is negative. So we end up with y equals 6 minus all of this stuff. And then now we're going to do the same thing we did with the constant earlier when we separated and differentiated. This whole thing we're just going to call C, and it's going to come out in front here. So the function ends up being 6 minus CE to the minus x squared over 2. So here's the function. So if you notice, this last term here looks an awful lot like our beginning exponential relationship. But we have the 6 minus it because of the 6 minus y in that expression times x. So, so here's the function that describes the differential equation. If we have an initial condition when x is 0, y is 2, we can find the value c here. So I'm going to substitute that in. I'm going to put the 2 in for y and the 0 in for x. E to the 0 is 1. So I'm going to end up with 2 equals 6 minus c. And when I solve that, bring the c over and bring the 2 over, c's got to be 4. So now I can put my 4 back here. So we have my function is 6 minus 4e to the minus x squared over 2. So here's my particular solution. This is my general solution. Remember, general solutions have just the constant of integration there. That represents the family. So here's the particular solution. And with that particular solution, we can graph that slope field. So we're going to, here's the differential equation. Here's my particular solution. You have all of that written down already. Here's slope field B that you did at the top of your page. And we're going to draw this particular solution. So we know we go through 0, 2. 0, 2 is right here. So we're going to put a dot at 0, 2. Mine's orange. Okay. And then we're going to go ahead and follow the slope lines. So we have horizontal slope lines here, and then they start sloping up, and then they get flatter. And remember, I mentioned that this is an asymptote because it has 0 slope. So they get flatter and flatter and flatter. And then you can see the symmetry, so the same thing happens on the left-hand side. So our function looks something like that with this initial condition. If we had an initial condition of like 10, then we would have something that would lay on top like that and not cross 6. So, you know, just to kind of keep that in mind. So there is our sketch for this function. So just to kind of summarize how we can use logarithms and exponents to solve differential equations. We separate the differential equation, we integrate, we use the properties of logs to solve. So the first 2 steps are the same that we've been working on all this entire unit. Really the new thing is using our log properties to solve for the function. And of course we have that special condition when we have dy dt equals ky, where we don't have any calculus involved at all. At this point, you can go ahead and start the homework for 6-4. It's only a 1-day assignment, so if you would like to take a proficiency quiz, you can also do that at this time.